So hopefully nobody is too hungry yet, but thank you all for being here. I wanted to start with a show of hands that I suspect may be very, very similar to that show of hands. But who here has used Istio? Okay, a couple. Anyone used GRPC yet? Good. Anybody used GRPC and Istio together? All right, excellent. I think that's exactly what I was hoping for. This talk is about my experience over the last several months working with GRPC and Istio together. Obviously, both of them are fairly new projects, or relatively new anyways, and so there was a lot of pain involved in getting them working, especially in being able to manage high throughput applications. So I'm hoping that by the end of this, anybody that's evaluating these two technologies, either independently or together, will save some time by knowing what to look out for and hopefully being able to work around some issues a bit more quickly after seeing this. To start with a bit of a background on myself, I've been in the industry for the last 20 years or so. Started in the software space, and then moved to operations when I realized I actually kind of liked being woken up in the middle of the night and getting an adrenaline rush. So that led pretty naturally into being involved in the Kubernetes community, having the operations and software background. And I started working with Kubernetes more actually on the AWS space, being a contributor to the KOps project. More recently, I started OpsGuru with some partners. We're a consultancy that specializes in big data and cloud-native technologies, as you'd expect. And as a Google partner, a Google Cloud partner, my role for the last couple of years now has largely been as a partner consultant with Google's PSO organization, where I've gotten to work on some fairly large projects, particularly on GKE and doing app modernization with Kubernetes and cloud-native technologies. So more recently, I've had a fairly fortunate experience of being able to work on multiple projects that all involved very similar technology stacks with quite similar goals. Obviously, the two of those technologies were gRPC and Istio, and the goals were typically to support high loads, high throughput applications. So that's what we'll be talking about today. I'm going to cover them in three distinct groups, sort of based on an aggregate view of how these projects would go and where we'd run into certain problems. Usually it started with getting Istio in certain shape and making sure we understood the performance characteristics of Istio as we scaled up. And then looking at more application optimization, trying to make sure we're pushing as much throughput through individual pods in Kubernetes as possible. And then I'm just going to end up with a very light section on setting up monitoring in Istio. Istio claims a lot around observability and monitoring and tracing. There's some gotchas to look out for there that I won't spend a lot of time given how much experience there seems to be with Prometheus in the room, but I'll point out the key areas. So let's talk about the Istio side. First off, I've promised to talk about pain points with Istio. It's easy to look at some of these setbacks that we ran into and think, well, why use it in the first place? Why not either remove Istio completely or write your own? I think for smaller microservice applications, that could be a viable option, going without a service mesh entirely. However, there's complexity in microservices themselves, especially when you start getting into moderate or heavy loads. A lot of that complexity comes around orchestrating deployments of dependent services. You start really benefiting from things like traffic shifting, blue-green deployments, canary deployments, all these things that Istio provides out of the box, and those features are generally fairly mature with it. So if you were to try to write your own, you'd quickly come into the situation where not only are you reinventing the wheel, but you're reinventing a wheel that is very critical to your entire system, right? It's implementing these cross-cutting concerns that if you get it wrong, it's going to have drastic effects across the board. It's actually even more important if you're in a regulated environment where security and compliance are key. A lot of our projects involve needing MTLS and strong authentication and really benefiting from some of the identity management that Istio provides. And then less critically maybe, but still just as important is the observability component. Having something that, like Istio, that provides a uniform mesh that's exposing statistics in a common way is very, very useful when it comes to debugging. So the key here is that yes, Istio is painful, especially at scale. It adds more complexity, but my argument is that microservice in general, you're going to have complexity one way or the other. It's really about picking the problems that you want to work with. So as I mentioned, our goal with Istio was typically to understand its characteristics as we scaled and make sure we had a decent baseline. So a standard setup for our initial tests would be to have a client that was capable of generating about 1,000 records per second. And generally the servers, we'd have one-to-one with the clients for initial testing and get a baseline that way. And our first goal was to be able to scale that up linearly, like I say, and that means that 200 clients should be able to sustain 200K of load without using relatively more resources, and especially without degrading the performance per pod. In actuality, the first thing we'd run into typically was a ceiling around 50,000 records per second. So we could scale up to 50 clients, usually just by doubling the number, and see the linear scalability there. But beyond that, we would start generating errors and have all sorts of issues pop up. So the first issue that we'd typically deal with was the next doubling of the workloads. You would see that the newer pods in the cluster start to crash when they started up. So you'd double the load, you would see all these pods come up, they'd fail, and they would start entering crash back-off loops where they kind of go into an exponential restart mode and all sorts of other issues. So some investigation into that led us to realize that a lot of the common bottlenecks in Istio were actually results of the control plane, which is not ideal. Typically, when you're trying to optimize your data plane so that the path that data is taking as it enters the cluster until it hits your workload, you want your control systems to be independent from that. Kubernetes generally does a good job of this, where problems in the Kubernetes masters or the control plane don't directly affect like workloads that are out there. We'll talk a bit about how particularly the pilot and then really mixer components of Istio can affect that data plane, which is obviously a problem. And then third in Istio, the horizontal pod autoscaling parameters are something that definitely need tuning from defaults. That is, it's a little bit more boring than some of the control plane stuff, but I think just as essential to get that working properly. So as I mentioned, as we're on our scaling up process, typically what we'd see first is these new pods failing. And after a bit of investigation, we were able to see that pilot was usually having its load increase proportionally with some of these problems and figure out what was going on. So to take a step back and look at what pilot does in the cluster, it's the part of the control plane that's responsible for shipping out route information and giving your Envoy sidecars a view of the cluster topology. So really, without that configuration, your pods are useless. So the first thing they do when they come online is the Envoy sidecar, the proxy in your pod, will reach out to pilot and pull down these configs. So as more and more pods start concurrently, you start putting more load on pilot, and eventually your pods are unable to pull down these configs. So that sends them into this retry loop. And if you have, say, 50 pods coming online at once, that the exponential back off causes at first a bit of a retry storm. So they're all retrying and still hitting pilot and still causing it to fall behind, sometimes to fail and restart itself. And usually what we'd see is, in this example with say 50 pods, it could take anywhere from 30 minutes to even 60 minutes before things would normalize and the last pod would come online. Once we identified what the issue was, the solution was relatively straightforward. The HPA parameters for pilot defaulted to having a minimum of 1, so you'd only have a single pilot instance as you started scaling up. Moving that to 3 spread sufficient load across for most of our testing and is generally recommended just for resiliency in production. So that was the first step. The other one was just, especially in QA and testing where you're doing a lot of artificial workloads or artificial scaling up, it's useful just to pre-warm this, to pre-warm pilot by scaling it up intentionally first. So just increasing the minimum so that you have that number of pilot instances available, and just follow a 1 to 50 ratio. So basically, if you know you're going to be spinning up to a new 200 pods, then just give yourself 4 pilot instances. So once we got pilot figured out, we'd be able to cross that 50K plane. The pods would start coming online correctly. You'd see everything behave, but then you would have, we'd start seeing degradation after around 80,000 records per second. And this degradation was usually followed or accompanied by errors coming back in the logs. Very strange behavior where you wouldn't see any errors on your server workloads, but you would see these errors in the client. And the metrics that we were collecting from Mixer, which we'll talk about in a bit, were incorrect. They would give you some like mix of counts between what your client was showing you and what your server was showing you. So with that, we again had to take a look at what the control plane elements were doing. And again, not obvious from the start because this issue is with your app, it looks like initially, and eventually you start seeing that, okay, Mixer is increasing in load similar to what Pilot was, but with slightly different behavior. So to look at what Mixer is doing in the cluster, as opposed to Pilot that's responsible for just pushing down these route configs, Mixer is responsible for, 1, collecting telemetry from all your Envoy proxies, and the proxies themselves generate telemetry and metrics that can be collected directly from Prometheus. Mixer tries to be more helpful and aggregate these into like cluster-wide total requests per second through your cluster, that sort of thing, or through your service mesh. And then more importantly, it's also responsible for policy checking. And the policy checking aspect is for things like if you've configured rewrite rules based on headers, if you've configured throttling or rate limiting, that sort of thing. Even though the sidecar will cache some of the data that it needs, it still creates these frequent round trips to Mixer to make decisions based on traffic and what to do with it. And that really creates a central point of failure and causes Mixer to become a serious problem as you scale up. So it's not so much how many pods are coming online at once as how many requests are going through your entire service mesh. So as Mixer would start to say heat up, or the CPU in particular would start to get highly utilized, there are circuit breakers within the control plane defined that would start throttling requests to the Mixer component. And these requests, the throttling would basically prevent the proxies from updating their caches in time to be able to serve traffic, and they would start rejecting traffic by either dropping it or returning 503s, and that's where we'd see some of the strange behavior. The fact that the traffic was being throttled and also contained telemetry is why we would see oddness in the metrics that we were collecting from Mixer itself. So that one was particularly ugly. Trying to scale out Mixer the way that we'd done with Pilot didn't work just because the load was so high on it. You'd basically end up with one mixer per workload pod under heavy load. And that was just a prohibitive amount of resources for us. So it took a bit of digging and working with the community, both in Istio and Envoy. But ultimately, it's become obvious that Mixer is inherently a single point of failure in these clusters. They're actually looking at replacing how this behavior works in Istio with what they're calling Mixer version 2. And that will push all this behavior, like the policy checking and telemetry collection down to the sidecar. So it's a much more invasive solution than with Pilot, but disabling policy checks and telemetry is the recommended workaround for now. That takes Mixer completely out of the process and allows the traffic to flow freely without requiring those round trips. So that step really gave us the linearity that we were looking for. It let us scale up to get that 200,000 records per second throughput. Unfortunately, it did mean we had to live without some of what Mixer provides. You can work around this right now, and it's every release. So we started this in Istio 1.1. It's now 1.3, and in each release they're doing a better job replacing these features. Mixer is now disabled by default in a lot of the installation methods. Some, like the Helm chart, last I checked, it was still enabled by default, so you want to double check that. But for working around these issues, for particularly whitelists and blacklists, as long as you're authenticating your traffic and giving your requests IDs, either through JWT or MTLS, you can use RBAC to restrict where traffic is going. And then for telemetry, there's two approaches. The Envoy native telemetry, which allows the sidecars or configures the sidecars to generate a subset of these metrics that would be missing, or mixerless HTTP telemetry, which totally moves that behavior down to the sidecars and will be the default in I believe 1.4, the next version of Istio. Both of those methods are described on the Istio wiki on GitHub. So though we had linearity in the Istio service mesh, the one issue that we're still running into was if we tried testing bursty traffic, especially around 15 or 20% sudden increases in traffic, we would start to get odd behavior again, both from Istio components as well as workloads. And it turned out to be that just the delays in horizontal pod autoscaling along with the initial configuration were insufficient to be that reactive. So for those that aren't aware, in Kubernetes, horizontal pod autoscaling basically is a controller in Kubernetes itself that you can specify these resource definitions for a given deployment, so a given workload. And the HPA resource basically says, here's your minimum, maximum values that you can oscillate between, and then you give it some metrics and their thresholds that will trigger a scale up when they're reached. The problem is that there's this inherent delay as you wait 60 seconds at a time for metrics to be scraped, and then another anywhere from 15 to 30 seconds usually for the HPA controller to check those metrics. So in practice, you can wait up to 2 minutes for HPA to take effect. And by default, Istio sets most of its components to an 80% CPU threshold, which means by the time that threshold is breached, especially if it's a real short burst, you often don't have enough time to wait for HPA to kick in. So the solution here is pretty straightforward. You drop CPU thresholds to 50%. Custom metrics are another option that we'll talk about how to enable that in Prometheus, but they let you define application metrics that may more correctly indicate how much load is on your app, as well as allow you to define more proactive metrics, things that might trigger scale-ups based on peak periods of day, that sort of thing. And then if you're running a self-managed Kubernetes, where you have access to the control plane, it is possible to change the HPA sync periods and some of the delays in that in the controller manager, but it's something to be done with caution because it can easily start to cause HPA to thrash a bit. So just to recap, this is how we get to the initial linearity with Istio itself, hitting that the 50,000 threshold first, then being able to get a little bit better with 80% by tuning pilot, and then getting up to that 200,000 mark finally by removing mixer. At that point, 1,000 requests per second through the application itself was not very impressive. We didn't want to have to scale up to 1,000 pods in order to achieve our 1 million metrics. So this is where we'd start looking at the gRPC and application communication side of things. So with gRPC in particular, the two key issues were generally around load balancing and understanding flow control. So I'll just give a quick overview of how streaming works in gRPC before we get into those, just to provide a bit of background. And again, looking at why you would use gRPC, this is a less clear-cut decision than, say, adopting Istio. If you're already using fairly mature tools, say REST-based tools, in your applications, then it may not be worth adopting gRPC. But what's compelling for a lot of teams as they especially implement new applications, new APIs, that sort of thing, is that gRPC provides some efficiencies both in the development cycle through code generation of stubs and clients. It removes the need for a lot of explicit transformations like you do in using REST calls. And then protocol buffers generally provide a pretty efficient wire format for communication. And then the streaming functionality happens at a couple layers in gRPC, but it's based on HTTP2, so it benefits from the request multiplexing that HTTP2 does, and it gives you that some efficiency in the communication. So there's some real benefits there, but again, it depends on how it compares to the tooling that you're using now. Looking at the key elements in setting up a bidirectional streaming gRPC call, the first element to be aware of is the concept of a channel, which really abstracts like say the TCP connection in one of these calls. So when you're establishing an RPC call, you'd create the channel with the name of the service that you're interacting with, and then you'd invoke your RPCs. If it's a simple request response, sort of old style remote procedure call that they call a okay, it's skipping my mind now, but if you're just doing that, then it would just send a single like request message and response message. In our case, we were using bidirectional streams, so it uses a long-lived HTTP2 stream for both the request and the response. So clients and servers are able to set up observers to watch their incoming stream while they're sending out messages asynchronously on the outbound stream. So not having to set those up and tear those down were a minor efficiency gain. In these systems, we're generally dealing with streaming data coming in, so it was a great fit. The first problem with gRPC streams came up when we started looking at the load balancing side of it, and we would find that as servers auto-scaled out in the back end, we would get these like bad distributions across the ingress gateways of Istio. So the ingress gateway is actually a pod that sits in front of your server pods that's bringing traffic into the service mesh for you. And so this example would be 30 minutes after a scaling event. The newer pods on the right-hand side would still have barely reached gotten any traffic, and the load on them would be extremely low. The reason for this is a bit more subtle. Something that I didn't show in the last diagram with the channel is that gRPC will actually is smart enough to resolve the addresses behind the server that you're connecting to. So in, say, something like Kubernetes, where you're getting multiple A records back for a service name, gRPC will set up what it calls subchannels to connect to each one of those back-end servers. And then as you create RPCs, it will bind each stream to a specific subchannel. So this is a client load balancing feature that it has that works really well when you're inside a cluster or when you have that visibility into servers directly. But it starts to break down when you have something like a cloud load balancer in the way. So in our case, we had this cloud load balancer. It was in GCP, so it was only getting one IP address returned. And so it would only create one initial connection, which created this hot spotting problem on the internal gateway pods. On the other side of the gateway, because Envoy is proxying those requests, you still end up with better load balancing, and that tends to behave well as long as the RPC calls themselves aren't too long-lived. If they are, then you have a similar problem within the streaming, within the stream side of things. So as you would expect, the solution is really just to make sure you kill that connection periodically, and likewise, if your streams aren't naturally like shorter lived, then putting an artificial cap on them, say 10 or 15 minutes, is recommended as well. But the way that you kill these connections it can vary by language, and it's not always obvious. In the GRPC Java implementation, it's relatively straightforward. You kill the managed channel, and that shuts down the underlying connections. It does let you gracefully deal with any of the streams that are in progress and kind of clean those up as you need to. But in other implementations, especially some of the C-based implementations of gRPC clients, they can share a global connection pool. So even killing the channel, you'll still end up with these long-lived connections running through your load balancer and creating hotspots on the ingress pods. So in the C-based ones, there's this argument to pass in to make each channel use its own local subchannel pool, which causes it to use its own local connection pool as well. So depending on what implementation you're using, it's worth digging into to make sure that it's actually going to have the effect you need on at the TCP layer. So once we fixed that bit, or basically caused our channels to recycle every 10 minutes or so, we got a much better distribution there. You can see that the P90 we basically dropped in this sample cluster by 60%. Standard deviation dropped by 70%. So it tightened things up, which meant we could then set more reasonable limits and requests on the ingress gateway pods and make more efficient use of those. So the next issue we ran into was with flow control, and it took a little bit to figure out what was happening here. In this example, we tried ramping the client pods up to send 6,000 records per second, but we would quickly see that the number of successful records would drop off and be replaced by errors coming back. Most of these would be timeout errors, but similar to when we had issues with Mixer, we wouldn't see any of this traffic on the server side. So to understand what happened, we had to dig into some of the flow control aspects of gRPC, which is really just the flow control aspects of HTTP2. And there were two primary issues that came out with that. One was the aggregate buffer size of the gRPC or HTTP2 buffers that Envoy allocates. So because with Istio we have this gateway in between us and the server, you're actually dealing with 3 buffers, whatever the client code has allocated, and then the buffer in the gateway and the buffer on the server. And then the other issue that we're worrying about was back pressure detection. So if these buffers start, or when these buffers fill up, making sure that the client is responding appropriately. We naively initially thought that the client would error out or block if you were trying to send in there was back pressure, but it turns out to be a bit more subtle than that. So first, for managing the buffers, it's important to understand how HTTP sets up the flow control, and it does this with a window size parameter. When you establish a new stream, the server advertises a window size to the client, and that tells the client how much data it can send. Obviously, if the server starts to fall behind and the buffer is filling up, then it starts sending a smaller and smaller window size until it hits 0, at which point the client should just stop sending. The problem was that Envoy's default buffer size for HTTP2 is 256 megs. So that meant we had half a gig of buffer basically between the client and the server. So we would send messages, and while the server started backing up, we wouldn't see that on the client at all, and things would be buffered long enough and live in the buffers long enough that the messages would time out before they even made it to the receiver. So the first recommendation was to drop those buffers to 64 kilobytes. The Istio team actually implemented some environment variables that Pilot will watch for to push these settings out to Envoy. So you need to set these two environment variables to control that buffer and make sure you're not allocating 256 megs per Envoy instance. So even with that, we found we still wouldn't get any errors. We could keep sending with the gRPC Java client and not see any back pressure in the client itself. And it turns out the issue is that if you don't call this isReady method, well, even if you do call it, but if you ignore this isReady method on the client, the gRPC Java implementation will actually allocate more buffer in the application memory space to just put your messages in a queue until they're sent. So the recommendation obviously is to check this isReady. The mechanism in gRPC Java is a little convoluted, so I've just got a snippet to show you the key elements here. This is not obvious, and it's not called out in much of their documentation, especially if you go to use gRPC. Like the initial docs looks like you just get a handle to the client and then send at will. In reality, you want to implement this client call listener, implement it's on ready, and then even within there, you need to check that the call is ready, because on ready is being called asynchronously, and can be a significant delay, and the call may actually flip into another state before you get there. So that's the important bits. There's obviously a bit more for error handling and that sort of thing, but it wouldn't fit on a slide. So just be aware that depending on the language you're using this from, the semantics may change a bit, but you're going to want to be aware of checking for that back pressure. So with those results, we basically dealing with fixing the back pressure issue and detecting it allowed us to find some of the tunings that were required, the adjustments to make on the server side, and allowed us to hit that 6,000 records per second limit without any errors coming through. In the end, this was a pretty typical setup for us. We'd have around 170 clients pushing through it at 6,000 RPS, and that would give us that 1 million number. And then for gateway pods, typically you'd end up with about 40 needed to support that throughput. But obviously those numbers are going to vary a lot based on your workloads and what your clients and servers are actually doing. This was all with very straightforward, like artificial load generators and servers on the back end. So with that, just a couple notes on issues that we found with the traceability and monitoring that Istio sets up by default. So I'll cover how we installed Prometheus, how we enabled custom metrics, and then some of the options for scaling it that came out. The key thing with Prometheus is disable the default that Istio wants to deploy for you. It's not production ready. It doesn't use a stateful set, so the data is not even persistent, and there's a number of issues with it. So replacing it is quite easy. We use the Prometheus operator within the clusters themselves. Obviously, if you're experienced with Prometheus and you've already gone through the pain of learning the configuration language, then that's a good option as well. The Prometheus operator in Kubernetes is nice because it has some custom resource definitions and custom resources that do a good job of abstracting most of the common configuration you'd make with it. As far as enabling custom metrics like we spoke about earlier, there's a Prometheus adapter that you can install in the cluster that basically pipes a specific set of Prometheus metrics that you define into the Kubernetes custom metrics API. And this makes those metrics available for auto-scaling like we talked about earlier. And you're then able to tune the Prometheus scrape intervals to get more frequent readings of those metrics to help speed up the HPA process based on those metrics. So the sort of de facto Prometheus adapter is this DirectX Man 12's implementation on GitHub. And then finally, given the level of experience in the room, I expect this is known by most of you, but for scaling Prometheus, you kind of have three options. One is just to scale it vertically, throw more resources at Prometheus. The other one would be sharding. So even scaling Prometheus vertically, we found most of our issues had to do with time series cardinality and the way especially certain teams wanted to collect metrics. So even scaling it vertically, the time series themselves were so had such high cardinality that that Prometheus couldn't keep up. So sharding was really the only option to cope with that. And again, as most of you know, once you've sharded Prometheus out, it's much more straightforward and more convenient to have a primary Prometheus that is federated with them. So it also allows you to define much lower retention periods on those sharded Prometheus, define recording rules to aggregate some of the metrics, and then just pull in the aggregate metrics for longer storage in that sharded Prometheus. So if you haven't used Prometheus before, I think it's good to keep these three strategies in mind, because whether or not you need them right from the start, typically as your system grows, you're going to need to implement some combination of the three. And then finally, just a couple notes. If you're using tracing, again, you don't want to use the defaults deployed by Istio. They actually now state that in the docs, but didn't previously. So disable that. You can use generally there's an operator for both Zipkin and Jaeger. Other options will have their own installation, but replacing the default is just a matter of setting it to false and then providing its address to the Istio installation method so that Envoy knows where to ship its trace points. And then make sure that you're setting that pilot.trace sampling rate to something low, like 1% or lower on a system usually, to make sure it's not really interfering with the performance of your system. Grafana, similar, although even easier, because if you're using the Prometheus operator, it will install a Grafana for you. So you just set the default to disabled. Though Istio does have some very helpful dashboards for Grafana, so however you've installed it, I recommend pulling those down from Istio's repository to give you mesh-wide dashboards. So just to summarize, it is possible to achieve this high throughput with the new technologies like Istio and gRPC, though there are several pain points you'll have to work through. It's just a matter of understanding how the control plane affects things and some of these trade-offs that gRPC give you. So I really hope that anyone that's evaluating or about to adopt these things, that this saves you some time if you bump into any of these odd issues. And if you've got other odd issues and war stories, I'd love to talk to you after the talk as well. So with that, thank you. I'll be at the OpsGuru booth for the rest of the conference, so if you have those war stories, please swing by and we can chat.
Thank you very much. Дорогие, соответственно, если у вас есть вопросы, то их нужно задавать сейчас. You have to choose best question.
Okay.
Thank you. And we have a present for you. Можно попросить подарок принести?
Oh.
It's book and.
Oh, nice. Thank you.
Yeah.
Thank you very much.
Hi. Thanks for a really interesting report. And the question is about the clients with RPS. How much do those clients correspond to real-life clients, say, working with a database? I guess the database will be a big bottleneck in achieving that kind of performance.
Yeah, in our case, it wasn't so much the wasn't so much the clients that were dealing with the database, but in a lot of these, the server itself would be taking that traffic in, and then, yes, bottlenecking at the database side. So that's where having some mechanism for transmitting the back pressure that the database may cause, right? Or even if you're sending to a Kafka cluster or whatever the sync is, being able to transmit that data, that back pressure all the way through to your clients, and coping with that in the clients was critical. So not having mature sort of strategies for dealing with that with their own exponential backoffs and that sort of thing, because we did run into issues as well with just application design creating its own retry storms on those. So.
Еще вопросы?
Yep. May I ask a question? I'm here, to the right.
Yes.
Yep. So yeah, thanks. It was really interesting. I was a little bit late, but regarding Prometheus scaling, you mentioned that sometimes metrics cardinality is a problem.
Right.
So from your experience, what is the limit? I mean, how many time series you have when you start having problem? You know, when vertical scaling doesn't work anymore.
So the numbers that we had were pretty insane when we ran into this problem. So we had one metric that ended up having about a cardinality of about 100,000.
Okay.
Right? So they're because it was being recorded on a request by request basis. And that, even throwing like a fairly significant portion of a big instance on GCE or GKE at it was insufficient for it to keep up. So the recommendation that I've seen is to keep cardinality on any given workload itself below about 100, right? So that then the assumption is you're going to have a number of on a workload, you'll have a number of those, right? So you'll probably multiply that by 100 as well for the number of pods or something there. So I think total cardinality, once you factor in everything, all the labels that are automatically being added, probably somewhere around 10,000 or something like that would be when you'd start to want to shard that out and then collect either from different workloads or do like horizontal sharding with it. But
Okay, thanks.
Hello.
Yep.
Yeah. Evgeny Booking.com. Thank you for a great presentation. And could you please describe about this thing when you were improving the feedback loop between the Java client and Envoy client by shrinking these buffers and checking and implementing this listener in order to keep this on ready state? How did you manage to get the root cause of this? Why it happened on the first place? I mean, for instance, did you implement some custom error handling or something like this? How did you manage to get to this 6K point? Do you think that the internal implementation is not as good as the custom one, or?
For us, in this case, it was really because the server was doing some checks with a back-end queue, and it was pretty trivial implementation with like the way it was dealing with a thread queue that was calling out to another service and just being too chatty with that other service dependency in the back end. So it was blocking more frequently than we were expecting and causing that back pressure. So it wasn't directly related to GRPC or to Istio in that sense. It was really just application level stuff. But it was more the GRPC flow control was preventing us from seeing clear signals of that in the client itself. So fixing the flow control just meant that the client had a more accurate view of what was happening on the server, and we could start seeing that it was not keeping up, and that's when we were able to go into the server and just focus on the Java code itself.
Okay. Yeah. Thank you.
Yep.
Thank you, Robin. Alexander Peterson, MTS. Robin, you were referring to the client optimization, and there was a little snippet. But what about the community? Is there some way to push this idea that the out-of-the-box gRPC client would be as smart as that?
Yes. So we actually worked with like most of the communities around these technologies pretty heavily, and so there was some sensitivity to trying to implement that in there. The problem is that there were some good decisions on why they made those choices, right? They wanted to give users the option of just sending and forgetting, and the assumption that there wasn't going to be that much back pressure. And now they've committed to an API, so trying to backport that. So they are aware of it. I'm not sure if there's plans to directly address it anytime soon. But it also is gRPC Java specific, like the Go implementation deals with back pressure a bit differently than that. So
thank you.
Yeah, thanks.
Hi, I have a question. Thank you for your presentation. You encountered so many problems with Istio on the beginning. It become a big investigation, and it brings diminishing returns, so you don't try to use a vanilla envoy and build something upon it by itself. And also I want to ask about your workload, what it was. Could you please describe?
So the workloads actually varied from project to project. Like this was kind of a sample that tried to pull together a few of those lessons. Generally, they were ingesting streaming data and then sending those off to like a data lake type system, right? So they'd go through another streaming pipeline after some transformation. So that's where like the back pressure being caused by dependencies on other applications or the data sync that you were sending to were a real concern. On addressing the question of why not just write your own control plane for Envoy, that on these projects there was enough time and they were in sort of an R&D mode initially so that we're able to work through these. I have been on other projects where they're writing their own control plane for it, using their XDS protocol for dynamic configuration of the control plane. The trouble is you quickly start building what Istio is and being susceptible to having those same problems yourself and implementing those same bottlenecks. So especially given that like a big fix for Istio is disabling the policy and telemetry checks. If you were going to build your own, those probably wouldn't be your first priority anyways, so you wouldn't have those features in that. And then it's really just a matter of scaling the other components. So for building your own, when we've seen folks do that, it's usually now you've got to build a controller to watch the Kubernetes API for resources to come available if you want to do any auto configuration based on services and that. So it's just a pretty significant level of effort unless you've already got something similar in your app, or if you're dealing with a smaller set of microservices where it's less essential to have a service mesh, then maybe not having a service mesh at all is an option. But like say in more substantial ones, I think the payoff of adopting a community solution and then just working through some of the problems is probably more clear cut. Thanks.
Thank you very much. It was the last question. And Robin, what was your favorite question?
I think the question about how we were optimizing the server side and dealing with back pressure, and that was I think that came from over here. Yeah.
Thank you very much.
Yep. Thank you. Thank you.